All right, so we're on page 19 of the notes. Before we left on Thursday, we were talking about how sometimes we have a strong base that reacts with a strong acid, and when that happens, the salt is considered to be neutral, acidic, basic. Neutral. It's considered to be neutral. If we have a strong acid reacting with a strong base, then my salt is going to be neutral. If I have a strong acid that reacts with a weak base, then my salt is going to be acidic. If I have a weak acid reacting with a strong base, then my salt is going to be basic. So the two things that you had to remember with this whole thing is that strong wins. So always remember that. Whichever one is strong, that's what type of salt it's going to be, which means that's what type of reaction that it's going to be. And we also need to remember that strong is a spectator. So we remember that strong is the spectator. So the first thing that we look at in the problem is we need to ask ourselves, look at the salt and say which acid and which base reacted to form it. Okay? So for example, I'm going to use NaCN. Okay, that's my example. There's my salt. Right? So I say, okay, which acid, which base reacted to form it? Your hint. The first one that is listed always came from your base. The second ion that's listed always came from your acid. Okay? So that means my Na came from what? Na, what would make it a base? OH. Thank you, Zach. Shut up. So it came from NaOH, which means my Cn came from what? My acid, so it would come from, what makes something an acid? That H in the front, so it would be HCN. Okay? So that's the first step. Yes, ma'am?
So like the base is always first and the acid always second, or?
It's because this one's always positive, this one's always negative. So the positive is going to bond with the negative hydroxide, and the negative one is going to bond with the positive hydrogen. See that? So the second thing I say is, okay, strong or weak for each one. So I'll look at NaOH and I say, is NaOH a strong base or a weak base? And I know that it is a strong base. How do I know that it's a strong base? Because Na is in column what? 1 bonded to hydroxide, so that makes it strong. So then I look at HCN and I say strong acid or weak acid? Weak acid.
Is it always going to be the opposite from a strong base and weak acid?
No, they could both be strong, but they'll never both be weak. Okay. So now we have to embrace the fact that strong wins, okay, and predict whether it's going to be an acidic or a basic reaction. So I look and say, since strong wins, this is obviously going to be what?
No, basic.
Basic, right? This is my strong base. So I know this is going to be a basic reaction. So if it's going to be a basic reaction, I go ahead and write my OH, I'll do it here, as a product. Because what makes something basic? Hydroxide, correct? Now, if it was going to be acidic, then I would have wrote an H positive, or I like to write an H3O positive, because if not, it just looks like your oxygen and your water disappeared, and it doesn't disappear. It's still there. Okay. But since it's basic, we went ahead and wrote our hydroxide. Then, step 4, we have to go with the fact that strong is a spectator. Okay? Are spectators included in our reactions? No. Okay, you should remember that from pre-AP. So therefore, which one of these was strong, the Na or the Cn? The Na. So if it's a spectator, we cross it out. The ion that is left over becomes one of my reactants. So I have Cn negative, and I always go ahead and put it in water. Do we see that? Okay. And then we write our product. And your product is always going to be whichever weak substance it came from. So since it was the weak acid that it came from, the weak acid is my other product. You should also be able to look at the equation and figure this out. If I put the Cn negative in water, and I ended up with hydroxide as one of my products, that means water had to do what? Donate a hydrogen, right? Where did that hydrogen go? To Cn. So I end up with OH negative and HCN. Do we see that? You with me? And sometimes, I know, my board is spastic today. I don't know what's up with it. Just close your eyes if you have seizures. All right, so sometimes we like to write water as HOH. What? When lights like blink really fast, it can cause people to have seizures. My board is doing that. As I'm saying, close your eyes when I go to scroll up and down if you have seizures. It's not a bad thing. Yeah, if you're epileptic. There you go.
Go quick, like.
All right. Sometimes, excuse me. Sometimes we like to write the H2O as HOH, just for the simple fact of sometimes then it's easier to see how that hydrogen got donated, and what I was left over with was the hydroxide. Okay. So it's up to you. I don't mind if you write it as HOH, but when you're on the AP exam, if you write it as HOH, once you get finished with the equation, can you please replace the HOH with H2O? I appreciate it. Thank you. So let's go down to,
Will they count it wrong if you put HOH?
I don't know. I just know it's not good scientific practice to put HOH. So.
Okay.
So let's go with exercise 20. Exercise 20 says, predict whether an aqueous solution of each of the following salts will be acidic, basic, or neutral, and prove it with an appropriate equation. All right, so now we get to go through our steps. We are so excited. Yes, we are. So A, I look at sodium acetate, and I say my sodium came from what? NaOH. Excuse me. Thank you. And so that means my acetate had to come from HC2H3O2, right? Okay. NaOH is a strong base. Acetic acid is a weak acid. So therefore I know this is going to be what? A basic solution. Because who wins? Strong wins. So I know I'm working with a basic solution here. So that means I'm going to go ahead and show my water. And I know that one of my products should be hydroxide because we said it was basic. Right? So now I say, strong not only wins, strong is also a spectator. So this sodium here gets crossed out. So my other reactant is going to be C3H2O3O2 what? Negative. Thank you, Amber. All right. Which means what's going to be my final product? HC2H3O2. Do we see that? Yes, ma'am.
So the water is acting as the acid in this situation.
Yes.
Okay. Even though that's already even though like it's a weak acid.
This right here, once it became that ion, it actually became a base.
Okay.
Remember? Because if I have HC2H3O2 and I get rid of that hydrogen, I donate it, then my acid becomes the conjugate what? Base. Remember when we did conjugate acid, conjugate bases? So that ion is actually a base.
So why is C2H3O2 negative as a reactant?
Okay? This is nothing but a net ionic equation. Remember we did last year, if it was soluble, if it was aqueous, we show it broken apart, and if it wasn't, then we showed it together. So let's look at this. So we have NaC2H3O2, which is aqueous, I know, because anything bonded to sodium is aqueous. So that means as soon as I put this, we added this to water, right? So as soon as I put this in water, it's going to become Na positive plus C2H3O2 negative plus H2O. It broke apart because it's aqueous. Remember doing this? Okay. So it goes back and forth to form, okay? My water breaks up. One hydrogen goes with my acetic acid. And then my OH that is left over would go to my NaOH. You still with me? Okay. Acetic acid is a weak acid, therefore it does not break apart easily, remember? So we wouldn't say that is aqueous, but NaOH is a strong acid, so it does what? In solution, breaks apart. So this would break apart into Na positive plus OH negative. Remember, what do we do with spectator ions? We cross them out. This never changed. It stayed the same, so it went away. So my net ionic equation is C2H3O2 negative plus H2O goes to HC2H3O2 plus OH negative.
That makes sense.
And then we still have the water.
You see that? And you still have your water.
Okay.
So it's nothing but a net ionic equation the same exact way we did last year. We're just kind of taking shortcuts instead of showing everything dissociated.
Oh, okay, so on the exam, will we have to do all that, or can we just show
You can just you can do it the shortcut way.
the super ones?
Does everybody see that? I don't know. If you don't remember your net ionic equations from last year, you might not, but it's okay. So let's look at B. So we've got NH4. Now remember, the first one always comes from my what? Base. What base does NH4 come from? Ammonia, which is NH3. Okay. So NO3 had to come from my acid, so that would be HNO3, right? Okay. Is ammonia a strong base or a weak base? Weak. Good job, Ty. And my nitric acid, my HNO3, is a strong acid. So, who wins? Strong. So what kind of solution is this going to be? Acidic. Still with me? All right. So now I'm going to show my H2O this time go into H3O positive instead of OH negative because this is acidic. Still with me? All right. So now we would say my strong is a spectator, so that NO3 goes away, so my other reactant is what? The NH4 positive. And what's going to be my other product? NH3. We feel good about this? This is not as bad as we thought? Alright, for the sake of time, we're going to skip C. If you want to try it and come back and ask me if you got it right, then you can. But I'm going to go ahead and move on to exercise 21. So, we're looking at exercise 21. And we say, okay, so that's great, that's fine, that's dandy, I can write the net ionic equation, but how is this going to show up in a problem on the exam? And it is going to show up as a problem on the exam more than likely, okay? And they're not just going to say, tell me whether this is acidic or basic. You're going to have to solve a problem using it. The good news is, this is literally just more of the same that we've been doing. So you can do this with your eyes closed. I promise you can. You really can. Alright, so let's look at exercise 21. Exercise 21 says calculate the pH of a 0.30 molar NaF solution And it tells me that the Ka value for HF is 7.2 times 10 to the negative 4th. Now, when I look at NaF, do I automatically think this was an acid-base reaction? No, you don't. So what is it about this problem? What in this problem do I look at and say that must have been an acid-base reaction? They gave me a Ka. They only give me a Ka or a Kb if I'm dealing with what? Acids and bases. So that's my clue that this NaF is an acid-base reaction. Everybody understand that? So now I've got to get my equation. I can do that. We just did this. So I know that Na came from what? NaOH, right? And I know that the F came from
Acid, the HF.
the HF. Okay? NaOH is a strong base. HF is a weak acid. Who wins?
Strong.
Strong wins. So what kind of reaction is this going to be?
Basic.
Basic. So I go ahead and show my H2O go into my hydroxide. Okay. I know that not only does strong win, strong is also a what? Spectator. So this sodium goes away. So my other reaction is F negative. And so my other product is
HF.
Good job.
Were you gonna have the rice table?
Now, we can go ahead and rice table this. My initial concentration of my fluoride ion is what?
0.3
0.30. Water does not count because it is a
liquid.
liquid. My product's originally 0. I'm going to lose X, gain X, gain X. I'm going to be at 0.30 minus X, X, and X. So my automatic next step that I'm thinking in my head is what? Set up my equilibrium expression, right? Right. But then, I'm smart. I'm real smart. And I know these people are trying to trick me because that's what they do. So I take a second look and I say, well, this is really funny. We've already said that this is what kind of solution? Basic, right? And we know it's basic because I've got what? Hydroxide as a product. So I know it's basic. And they gave me a what? Ka. That's not going to work. I don't need a Ka. I need a Kb because we're dealing with hydroxide. But then I remember that Miss Snellick, being the great, awesome, wonderful teacher that she is. All right, Zach, it wasn't that funny. All right. Told me on page 8 of my notes when we first started this journey together on acid bases that Kw is 1.0. We forget that 8 there. Times 10 to the negative 14th. And she also told me that Kw is equal to Ka times Kv. So therefore, if I know Kw and I know Ka, I can find what? Kb. Yes, ma'am.
For the pH in the problem, can you just do the Ka in the opposite log and not pH? So you not be plugging
You plug in the concentration of hydrogen ion to get the pH. So that's why that wouldn't work. So let's go back to where we are on page 20. My shirt's hooked.
I like your outfit. Miss Nelly.
Hold on, we're having technical difficulties. We're good now.
They understand, trust me.
Okay, so now that I know I need Kb, so I set this up and I say, well, Kw is equal to Ka times Kb. So if I want Kb, that means Kb is equal to Kw divided by Ka. Am I right?
Yeah.
I am right. Kw is 1.0 times 10 to the negative 14th divided by my Ka, which is 7.2 times 10 to the negative 4. So then if I work this out, you should get that your KB is equal to 1.39 times 10 to the negative 11th, if you put that in your calculator.
Now,
So now I can solve for x. Okay? So we'll write our expression, but from here on out we're not going to write it. Okay? So KB is equal to my concentration of my hydroxide times my concentration of HF, all divided by my concentration of F negative. Okay? So now I say, well, my KB I already know is 1.39 times 10 to the negative 11. I'm going to get x squared on top, and I'm going to get 0.30 minus x on the bottom. What's my next step? What am I going to do with that x? Neglect it. And not only am I going to neglect it, I'm going to show that I neglected it, because I have to do that on the AP exam. Some of us are missing points on quizzes because we just absolutely refuse to do what I taught you to do, like neglect x. Some people lost a point on the last quiz because we just refused to draw an arrow and say neglect x. It's that simple. We got to neglect x. Our next step is to cross multiply. And so then you should get that x squared is equal to 4.17 times 10 to the negative 12th. So then to solve for x, I'm going to square root it. So I get x is equal to 2.04 times 10 to the negative 6. Now, my x gave me my concentration of what? OH negative. How is that going to help me get my pH?
POH and then subtract it from 14.
There you go. So I'm going to find my POH, because this is equal to my concentration of hydroxide. So I'm going to say POH is equal to opposite the log of 2.04 times 10 to the negative 6. So then my POH is 5.69. Everybody still with me? So then my pH is going to be equal to 14 minus 5.69, which is 8.31. We've also been missing points because we refuse to learn our rules for significant figures on pH. Okay? How many sig figs is right here in 0.30? 2. How many sig figs are right here in 7.2? 2. So my lowest number of sig figs is 2. So that means how many decimal places do I need for my pH? 2. I know they're useless. If I would have written the AP exam, I wouldn't care about the significant figures. Does that help? I wouldn't care. I know. And they just keep showing up everywhere we go.
Why can't we all just say 3?
I miss the days when we just rounded to the tens.
Right, yeah.
I just miss the days.
I miss the days where there were just only whole numbers.
Yeah, everything was a whole.
I agree with you, Jack.
If you didn't get
There
it,
were
Well-
no letters and they were all.
There is no limit.
All right.
It's that much.
Back to this. Exercise 22.
Play those games.
Exercise 22 says calculate the pH of a 0.10 molar NH4Cl solution, and the Kb value for NH3 is 1.8 times 10 to the negative 5th. Okay. So I see that they gave me a Kb, so it's an acid-base problem. So I know this NH4Cl had to have come from an acid-base reaction. So I go the easy way, and I say, well, the NH4 had to come from what? NH3, which is ammonia, which is a weak base. The Cl had to come from HCl, which I know is a strong acid. Who wins? Strong wins. So I know my H2O is going to form my H3O positive. Strong is also a spectator. So my Cl goes away. So my other reactant is NH4 positive. And my other product is NH3. So I go ahead and set up my rice table. Say I started with 0.10 of that. My water doesn't count. I started with 0 of my products. I lost X. I gained X. I gained X. I was at 0.10 minus X. X and X.
Will we get points coming off when we skip between those steps? And just went straight to 1.10 minus X.
I don't care if you show the rice table or not.
Okay.
So, I notice this lets me know it's what kind of solution? Acidic. They gave me what? KB. I can't use KB. I need what? Ka. But I'm smart. So it does not stress me out. No, it does not. Because I know that Ka is just equal to Kw divided by Kb. So I say 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th gives me a Ka of 5.56 times 10 to the negative 10.
Yeah.
Woot, woot. Thank you, I'm proud of myself. So now that I have a Ka, can I solve for X? Absolutely. I'm saying my Ka is 5.56 times 10 to the negative 10th is equal to X squared. I know I skipped the expression. It'll be okay. 0.10 minus X. Does everybody recognize this is my Ka? Is equal to my concentration of my products squared over my concentration of my reactant. What do I do with X? I neglect. So then I cross multiply, and I get X squared is equal to 5.56 times 10 to the negative 11th this time instead of the negative 10th. Then I take the square root and I see that X is equal to 7.45 times 10 to the negative 6th. X gives me my concentration of what? Hydrogen ion, right? Remember H3O positive and H positive are the what? Same thing. Okay. H positive and H3O positive are the same thing. So how can I find pH now? pH is equal to opposite the log of 7.45 times 10 to the negative 6. So my pH is 5.13.
Oh, that's just my pH by 14 minus what?
Only we had to do 14 minus that up there because we found the pOH.
Okay.
This time I went directly to pH because I already had my concentration of hydrogen. Everybody see it? Everybody got it. Okay. Exercise 23 is more of the same with the exception of it's going to be an acidic reaction and they give you Ka so you can stick with the Ka. You didn't have to find Kb. I'm going to skip it. If you want to work it and then ask me if you got it right, you're more than welcome to. Hopefully you can send me a picture if you want to work it, and I will respond with whether you got it right or not. So now let's skip. We have been talking about the Bronsted-Lowry concept of acids and bases, okay? Where the acids do what? Donate a proton, and the bases accept a proton. With the Lewis concept, they switch, and instead of donating protons, we're going to start talking about electron pairs. So since protons and electrons are opposite, just think of it as the acids and the bases also do opposite. So acids accept a pair of electrons, and bases donate a pair of electrons. Okay? Now, what? To remember this, we've got to remember how to draw our Lewis dot structures. Okay? Which, from the looks on our faces, we don't remember from last year. But it's okay. When we have to ask what it is, we definitely forgot.
I'm really good. Wait, is this the thing where you do dot, 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 dot?
Alright. Shh, excuse me. Excuse me. It is okay because we're about to learn how, and it is not stressful. It's really not. I promise.
I can do one element.
All right, so let's talk about how they drew BF3. This is going to come back to you, I promise. Okay? Boron on the periodic table is in what group?
13.
13. So how many valence electrons does it have? 3. So I say 3. Plus, fluorine is in group 17 on the periodic table. So how many valence electrons does it have? 7. And I'm going to multiply that 7 times 3 because how many fluorines does it say I have? 3. So 3 plus 21 is what? 24. Okay? That means when I draw this, I should have a total of 24 electrons. But we always draw our electrons in what? Pairs. So I'm going to divide this by 2 and say that means when I get finished with this drawing, I should have 12 pairs of electrons. Are you still with me? Absolutely you are. So, who, by looking at BF3, who would I assume is in the middle?
B.
B, my boron. So I take my boron, I put him in the middle. Okay. I go ahead and draw bonds to all of my atoms that are on the outside. Okay. So remember, each line represents how many electrons? A pair of electrons. Okay, now don't draw those pair of electrons. I just did it there so you can see that they are a pair of electrons, but would you include that in your drawing? No. Okay. Now, so once I draw, so there's 1, 2, 3 pairs. Okay. I go ahead and give all of my outside electrons a total of how many?
9.
8. Remember, everybody wants how many electrons?
I'm just saying it's gonna be non-pairs.
8. Okay, so I'm gonna go 1, 2, 3, 4, 5, 6, and then this line here would be what? 7, 8, right? So I've already got 1, 2, 3, 4, 5, 6, 7, 8.
6.
Then I've already got 1, 2, 3, 4, 5, 6, 7, 8.
That's 9.
Do we see that? Alright. So if I count these up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs of electrons. That means I'm done with the drawing. Everybody see that? So let's look at ammonia, which is in H3. Nitrogen is in column 15, which means it has 5 valence electrons. Plus, hydrogen is in column 1, which means it has 1 valence electron. I'm going to multiply that times 3 because I have 3 of them. 5 plus 3 is 8. I'm going to divide that by 2, and that means I need 4 pairs of electrons in this drawing. Yes. Yes. So, I'll say I put my nitrogen in the middle. I show it bonded to 3 hydrogens. Am I going to put any more lone pairs around hydrogen? No, because remember, hydrogen is your exception to the rule. It's happy with just how many? 2. So it's got its 2 right here in the bond already. So that means I have 1, 2, 3 pairs drawn. I need how many? So I need a lone pair, and instead of it going on any of the hydrogens, my lone pair goes on top. Do we see this? So now, Lewis acids accept an electron pair. Lewis bases donate. Who has the pair to donate? My NH3. So that's going to be my Lewis base, and my BF3 is going to be my Lewis acid. So they're going to come on here. Remember, this is like showing up to the party with nothing, but yet you eat and drink anyway. Okay, that's what happened. Okay, nitrogen brought all the snacks. Boron didn't bring any, but it partied anyway. So then what I get is this bond right here, which is not the same thing as the bond here. Okay? Because, remember, nitrogen has 5 valence electrons. Hydrogen has how many? 1. right? So hydrogen donated 1. So nitrogen had 1, hydrogen gave 1. Nitrogen had 1, hydrogen gave another. Nitrogen had 1, hydrogen gave another. So do you see how they're sharing equally? Nitrogen brought 1, hydrogen brought 1, we shared. Here, boron brought none, nitrogen brought both of them. So we don't just call it a covalent bond, we call it a coordinate covalent bond. Do we see the difference between a covalent and a coordinate covalent? Yes, we do. Right. So let's go to exercise 24. Exercise 24 says, tell whether each of the following is a Lewis acid or a base and draw the structures as proof. Alright. So let's start with A. So we have pH 3. Phosphorus is in column 15, so it has 5 valence electrons. Plus, hydrogen is in column 1, so it has 1 valence electron. But I multiply that times 3 because I have 3 hydrogens. 5 plus 3 is 8. 8 divided by 2 is 4. So when I draw this, I should have 4 pairs. So I go ahead and put my central atom, P. I show my 3 hydrogens bonded to it, but that only gives me how many pairs of electrons? 3. So my extra one has to go on my phosphorus. So is this going to be a Lewis acid or a Lewis base?
Lewis base.
How do I know it's going to be a Lewis base? Because it's got a lone pair on the central atom. Easier than we thought?
A little bit.
A little bit? Alright, I'm going to erase it so it doesn't get messy. So does everybody have this? No double bonds today. We'll save
Just
that for the
today.
next unit.
Today.
Alright, let's look at B. BCl3, I'll go ahead and tell you so we can save some time, is the exact same thing as BF3 up here, except instead of having fluorine, we have Cl. Okay, same draw. Yes, ma'am?
Would you send David Simmons to the office? She's gonna be checking out.
Yes, ma'am, I will.
Thank you.
So now let's skip down to C. We have H2S. Hydrogen has how many valence electrons? 1. We're going to multiply that times 2. Plus sulfur has how many valence electrons?
6.
6. So 2 plus 6 is 8. 8 divided by 2 is 4. Who's going to go in the middle?
Yes.
Sulfur. I'm going to show it bonded to my hydrogens, but that's only how many pair of electrons? 2. So where do my other 2 pairs of electrons go?
On the top and bottom.
There you go, on my sulfur.
Will they go like that? Or does it really matter where we put this?
It doesn't really matter. You could draw like 1 pair on top and 1 pair on bottom, but remember that would be the same thing as oxygen, where we draw the lone pairs like that. Because we're going to get to this in the next unit. It's a tetrahedral molecule. Remember, my lone pairs are sticking up in the air, and they're causing my hydrogens to bend down.
It's not like that.
We're going to get to it, don't worry. Alright, is this going to be a Lewis acid, Lewis base?
Lewis base.
Lewis base. Now, D is the only one where we start to get a tad bit tricky. But we're not going to let it phase us. Okay? We're not going to let it phase us at all. So, sulfur has how many valence electrons? 6. Plus fluorine has how many?
7 times.
And I'm going to multiply that times 4. 6 plus 28 is 34. And 34 divided by 2 is 17. So I know I should have 17 pairs. Who's gonna go in the middle?
Sulfur.
Sulfur. So I'm gonna show it bonded to my fluorines. What's my next step?
Add those, the dots.
Put my lone pairs all around my fluorines.
1, 2, 3, 16.
So if we count it up, it's 4, 4, 4, and 4, which gives me a total of how many?
16.
16, which means I have a lone pair left over. Where do they have to go?
They have to go on the sulfur?
On the sulfur.
That's weird.
Okay? And it's weird because we think everything can only make how many bonds? 4 for a total of 8 electrons, right? But if you remember, once you get to this third period on the periodic table, this is the first period, second period, third row on the periodic table. Once you get to this third row over here, we're going to get to this when we start doing our electron configuration. Okay? Once you start getting this 3p, they can make an extra bond. They can actually make 2 extra bonds because they can move into that d orbital. Don't stress about that. Read that next unit. You already know this. I promise you just don't realize you know it. Okay. Lewis acid, Lewis base.
Lewis base.
Lewis base because of this lone pair. And technically, if we forced it to, it could accept another pair here. So it could be a Lewis acid as well. The ones they will try to get you on is sulfur because it can form 6 bonds. And they'll try to get you on boron because boron only wants to form 3.
Now, well, when we're doing this, will it never be like HSF4 or something like that?
They'll keep it simple. They won't go, we say like it won't go beyond the scope of the course is what they call it. Okay. All right, exercise 25 right quick. I'm just going to skim through this. We're not going to go in depth with this. Is you have to identify the Lewis acid and the Lewis base. Anytime I see that positive, that should give me a clue that that's the Lewis acid. Okay? Because remember, they're looking for what? Electrons. So since they're positive, I know they're going to want those electrons. So that means this is my Lewis base and this is my Lewis base. And I should know that because if I draw out ammonia, it looks like this. And if I draw out water, it looks like that. They both have those extra lone pairs to give, which makes them Lewis bases.
Okay.
So do we have like conjugate Lewis acids and conjugate Lewis?
You don't have to worry about that.
Good.
All right, we're done for today. Y'all have a great and wonderful day. No homework tonight.
Do we have a quiz tomorrow?
No quiz tomorrow.
We just have to take the
You need to see.